proceed further and find the center of gravity if one of the mass is 4 kg and the other mass is 1 kg. Once again, we can assume them to be connected by a massless rod, and this distance is given as 10 meter. So now we know that is, if we have to balance the whole thing, it should not be right in the middle, but somewhere over here. Let's say it is over here. We say F, we take this distance as x, and this is 10 minus x. So this distance is 10 minus x is this distance. Now as usual, that is, we draw the forces, that is, this is 40 Newton and this is 10 Newton, M into G, M into G. Now once again, CG is that point where we can balance the whole body, where there is no rotation, no translation. So let's first deal with the translatory motion. So there is no acceleration, so it means net force along y-axis onto this, the whole system is stationary. There is no acceleration of this along the y-axis. We are balancing it. That is the basic definition of center of gravity, where you can balance the whole body or where you can balance the whole system. So that's why summation of force along y-axis should be equal to 0. It means this net force along y-axis should be equal to 0. So it means upward forces should be equal to 40 plus 10. 40 plus 10, that is, this should be equal to 50 Newton. Also, net torque about C should be equal to 0. So this means the anti-clockwise torques should be equal to clockwise torques. If we take this C as axis of rotation, then the torque of this force obviously about this is going to be equal to 0. The torque of this force, that is 40 into x, let's write it directly as 40 into x, should be equal to the clockwise moments because of this force about this axis. So it is 10 into 10 minus x. So this comes out to be 40x, or this comes out to, we can say, 4x is equal to 10 minus x. So this goes over here, 5x is equal to 10, so x becomes equal to 2 meter. So from here to here, that is 2 meter is this distance, and from here to here, it is the 8 meter is this distance. So this way we can find the center of gravity. So far we have found the center of gravity distance from one of the bodies or one of the particles. We can also find the center of gravity with respect to origin in Cartesian coordinate system. Let's say for simplicity we have 2 point masses which are lying on the x-axis itself. One is lying at a distance x1 from origin and the other is lying at a distance x2 from the origin. So its coordinates, if we say x, y, z, so it is x1, y is 0, z is 0. So this is x2, this is 0, y is 0, so this is also 0. Right now we are just okay with this, that is the distance they are going to be x1 and x2. Now let's go by the basic definition of center of gravity, that is at center of gravity we can balance the whole system of particles or system of bodies. To find the center of gravity, it is not necessary that these particles they should be connected to each other. So what we do is, to understand center of gravity, we just connect them by a massless rod or so, and then we try to balance it where the whole system can be balanced. So let's say over here we balanced over here, and we say this is the distance where we can balance the whole thing, that is M1 and M2. They are connected by, let's say, by this massless rod, and over here we are applying a force, and so that the whole system balance, that is about C, there is no translation, there is no rotation. That is what we have been doing. Now we are interested in finding this x from, let's say, origin. With respect to the origin, what is the value of x, that is where is the center of gravity with respect to the origin. So over here once again m1g is in this direction and m2g is in this direction. Obviously earth is going to pull all the objects towards center. So net force once again is equal to 0. It means F should be equal to m1g plus m2g. That is for translational equilibrium. So now for the rotational equilibrium. Now so far what we are doing is we have taken the torque about C, and we are finding this distance or this distance, that is what is the distance of center of gravity from one of the point masses or one of the bodies. Now let's take the torques about this z-axis. So about this z-axis, if we say, so this is x-axis. Over here you have over here we have two particles, m1 and m2g. So this is nailed over here. So now if you take the torque about z-axis, m1g, this force is trying to move it this way, m2g is trying to rotate it this way, that is once again clockwise direction, whereas this force is trying to rotate this system in the anti-clockwise direction. Once again about the z-axis, the system is in rotational equilibrium. It means the clockwise torques about z-axis is equal to anti-clockwise torques about the z-axis. Over here if you see, that is m1g is, this force is trying to rotate it this way, that is in the clockwise direction. Similarly, M2G is also trying to rotate this system about z-axis in the clockwise direction, whereas this is trying to rotate it in the anti-clockwise direction. So once again, that is torque about z-axis is equal to 0, net torque about this is equal to 0, because by the basic definition of center of gravity, this is the whole thing is balanced. It is translationally also, it is rotationally also, it is balanced. That is, net force is equal to 0 and net torque also equal to 0. Net torque is equal to 0 about this axis also, about this axis also, about this axis, any axis about this is equal to 0. Had it not been 0, then it would have alpha about that axis. But right now we see that is this is alpha is equal to 0 about any axis. So when the whole thing is balanced over here, now we take the torque of this mg about this. It is m1g force into perpendicular distance between line of force and acceleration. This line of force, this acceleration, this is the distance. So m1g into x, that is movement of this force about this axis. What about the movement of m2g about this axis? So plus m2g, this is the force into perpendicular distance between line of force and acceleration. That is, this is the distance. What is this distance? This is x2 only. That is x2. So this is, what is this? This is clockwise movements should be balanced by anti-clockwise movements. What is that? F into x. We have to find the value of x, because this is the point we are assuming that is where the CG is there. So x is going to give us the coordinates of center of gravity. So when we say it, so this comes out to be, so from here we can put F is equal to what? But F is equal to m1g plus m2g. So let's put F as m1g plus m2g. We see over here that g can be taken out common and it can be cancelled. So it comes out to be m1x1 plus m2x2 over m1 plus m2 is equal to x. This is, we get the coordinates of the center of gravity. Similarly, if you have a system of more than two particles and then let's say they are lying anywhere. So this is, let's say, m1, this is m2, this is m3. These three particles, they are there with their respective coordinates as x1, y1, x2, y2 and x3, y3, or we can have a z3 also, x1, y1, z1, x2, y2, z2, and this is our x-axis and this is our y-axis and this is our z-axis. Over here, as we have taken the torques about the z-axis and we have taken that is clockwise movements is equal to anti-clockwise movements. Similarly, if the body is balanced, it is not rotating about the x-axis also, about y-axis also, about z-axis also. So when we take these torques like this, we can easily do this. That is, x coordinate will come out to be m1x1 plus m2x2 plus m3x3 over m1 plus m2 plus m3. And similarly, y coordinate will come out to be m1y1 plus m2y2 plus m3y3 over m1 plus m2 plus m3. Similarly, z coordinate of center of gravity will come as m1z1 plus m2z2 plus m3z3 over m1 plus m2 plus m3. So this way we can get the coordinates of CG with respect to the origin in Cartesian coordinate system.